Yeah, good morning, my dear students. Today I am going to discuss the topic on spectroscopy, particularly infrared spectroscopy and its principle. Right? So, what is this infrared spectroscopy? Infrared spectroscopy, there are three divisions. What is the major role of infrared spectroscopy in drug analysis, particularly to identify the functional groups? Whenever you are going for any drug molecule, if you want to identify the functional groups, the ultimate method of analysis is infrared spectroscopy. So when we talk about the infrared spectroscopy, there are three basic regions in infrared spectroscopy. One is the near IR region, another one is the mid IR region, and the third one is the far IR region. And the corresponding wavelength is observed as 0.8 to 2.5 micrometer for near IR region. And in wave number, when we express it, it is 12,500 to 4,000 centimeter inverse. Whereas mid IR region is ranging from 2.5 to 15 micron, and the wave number is ranging from 4000 to 667 centimeter inverse. The far IR region is from 15 to 200 micron, in which the wave number is coming from 667 to 50 centimeter inverse. So why they have classified the infrared region into three categories: near IR, mid IR and far IR. The mid IR is the most important range. The mid IR is used for identifying the functional group of most of the organic compounds. So for analyzing any drug molecules and organic compounds, the mid IR region is very, very important. Whereas the near IR region basically is used for identifying the packaged material, particularly clinical packaging supplies, raw material packaged material, raw material packaging, or any material which is analyzed in a non-destructive manner. Without opening the packet, if you want to analyze that spectral characteristics, then we are going for near IR spectroscopy, particularly with excipients and other aspects we are doing with near IR spectroscopy. Whereas the far IR region is especially meant for inorganic compounds, particularly with metal ions and metal coordination compounds, as well as for some of the gaseous atoms like ozone or gaseous oxygen. These type of molecules, if you want to absorb infrared radiation in infrared spectroscopy, we are using this far IR spectroscopy. So therefore, for ourselves, for drugs and other organic functional groups are concerned in identifying the structure of the molecule, the mid IR region is very, very important for us. This is the way we are classifying the regions of IR, but generally based upon the functional groups, we are classifying the regions into two groups. One is the group frequency region or the functional group region, and the other one is the fingerprint region. So the functional group region starts from 4000 to 1300 centimeter inverse. That is the functional group region. Most of the organic functional groups will be observed in this region, and they give the sharp band in the spectra. Whereas if you go for this other fingerprint region is a very unique region for identifying every molecule, because even though it is densely populated, each and every molecule is having a unique fingerprint region. So the fingerprint region of the molecule will be ranging from 1300 centimeter inverse to 910 centimeter inverse. So this is some general view of the infrared spectroscopy. As I told, what we are studying in infrared spectroscopy, here the energy is little less as compared with the UV region. So in infrared spectroscopy, the molecules will go for rotation followed by complete vibration in the structure. So vibration in the sense, basically they are going for stretching and bending vibrations. And in infrared spectroscopy, we will study the complete vibration pattern of the molecule. Right? Now, what is the criteria for this infrared spectroscopy? All the molecules will not absorb infrared spectroscopy. The molecule which have the change in dipole moment during vibration in order to observe the infrared radiation. The molecule must have some change in dipole moment during vibration in order to observe the infrared radiation. So this is the criteria for the molecule. And this dipole moment is given by the terminology mu, which is equal to Q into R. What is this Q? Q stands for charge of the molecule, and R is the distance between the charges, or the separating distance between the charges, right? And mu is the dipole moment, right? So this dipole moment will be different for different type of molecules. For example, if you take a diatomic molecule, hydrogen, oxygen, nitrogen, chlorine. So they have same type of atom, hydrogen with hydrogen, oxygen with oxygen, nitrogen with nitrogen, chlorine with chlorine, right? So there is a symmetry here. So here there is no charge separation because the electronegativity of each atom in the bond is same. Here there is no charge separation because the electronegativity of each atom in the bond is same, and therefore what will happen, they don't have any dipole moment, right? When they don't have any dipole moment, simply we can say that the symmetrical diatomic molecules do not absorb the infrared radiation. So this is another important criteria, right? Now, generally, as I told, the vibrations, there are different type of vibrations. As I told, we are going to discuss about the basic vibrational pattern as well as the mode of bending vibrations or the mode of vibrations, right? So when I talk about the mode of vibration between carbon and hydrogen in alkene, for example, if I want to discuss the mode of vibration between carbon atom and hydrogen atom in alkene, so basically I told there are the basic fundamental vibrations are classified into two different types. One is stretching vibration and the other one is bending vibration. So stretching vibration is concerned with bond length change, whereas bending vibration is concerned with bond angle change. That is the reason bending vibration is also called as deformation. And stretching vibration, the energy will be higher, and for bending vibration, the energy will be lower. Is it clear? So generally energy is directly inversely proportional to wavelength, but in case of infrared spectroscopy, the energy is directly proportional to wave number, nu bar, in centimeter inverse, right? So if the energy is more, the wave number also will be more. So what will happen in case of mode of vibration? We are classifying the stretching vibration into symmetrical stretching and asymmetrical stretching. There are two types of stretching vibration. One is symmetrical stretch, another one is asymmetrical stretch. What is the meaning of symmetrical stretch? The carbon atom is present. Here it is bonded to the molecule, the carbon atom, and on the other side there are two hydrogen atoms. Now if you look at the symmetrical stretching, both the hydrogen atoms are away from the carbon atom. Can you see the arrow? Both the hydrogen atoms are moving away from the carbon atom. So there is a symmetry here, uniformity present. So therefore it is called symmetrical stretching. Whereas in case of asymmetrical stretching, one of the hydrogen atom is moving away from the carbon atom while the other hydrogen atom is moving closer towards the carbon atom. So there is no uniformity here. This is called asymmetrical stretching. So asymmetrical stretching is very, very important in case of IR vibrational pattern, right? Now when I come to bending vibration is concerned with a change in bond angle, right? So change in bond length means definitely more energy is required, right? Whereas change in bond angle means slightly we are rotating our head. Only there is a slight change in the bond angle. So energy also is very, very lesser for bond angle change, right? So bending vibrations are classified into two different types. One is called in-plane bending vibration. Another one is called out-of-plane bending vibration. What is in-plane bending vibration? So there is some symmetry or uniformity in the in-plane bending vibration during the bond angle change, and this in-plane bending vibration is divided into two types. One is called scissoring and rocking, and if you consider the out-of-plane bending vibration, there are two different types. One is called wagging and twisting. So what is called scissoring? If you look at the scissoring, the hydrogen atoms are just rotating. Both the hydrogen atoms are rotating closer towards the carbon atom. If you look at here, both the hydrogen atoms are rotating closer towards the central carbon atom, in which there is a change in bond angle. This is called scissoring. Just like a scissor we can see here, right? Whereas in case of rocking, one of the hydrogen atom is moving away from the carbon atom with a change in bond angle, while the other is moving closer towards the carbon atom, right? So this is called rocking. Basically it is called rocking, right? Then when we compare the out-of-plane bending vibration, there are two important things. Basically out-of-plane bending vibrations are observed in three dimensions. When you are keeping a plane of paper and how it is perpendicular, the atoms are perpendicular, we are going to discuss in out-of-plane bending vibration. And this is a very important vibrational pattern for, especially for your aromatic compounds also. So when I talk about the out-of-plane bending vibration, one is called wagging. That means both the hydrogen atoms are lying below the plane of paper and perpendicular to each other. Okay. So that is the reason I am giving the plus sign here. Both the hydrogen atoms are lying below the plane of paper and perpendicular to each other. I cannot show it here because in 3 dimension only we can able to see this wagging pattern, right? Whereas in case of twisting, one of the hydrogen is lying below the plane of paper and another hydrogen is lying above the plane of paper, right? So therefore it is called twisting phenomena, right? So both wagging and twisting are coming under the out-of-plane bending vibrations. So these are the fundamental types of vibrational pattern taking place in infrared spectroscopy. One is called stretching vibration, another one is called bending vibration. In stretching there are two types, symmetrical stretching followed by asymmetrical stretching. Whereas in bending vibration, one is in-plane bending and the other one is out-of-plane bending vibration. Again they are subdivided into different categories as we have discussed just now, right? Now when we talk about these other patterns taking place in other molecules, When we look at this diatomic molecules, for example, if you look at the diatomic molecules having different atoms, already we discussed diatomic molecules having similar atoms, where there is no net dipole moment, right? When I take the diatomic molecules having different atoms like hydrogen chloride, carbon monoxide, they have the dipole moment. Why? Because hydrogen, chlorine are different, carbon, oxygen are different. They have the dipole moment and they are expected to absorb the infrared radiation, right? Whereas some molecules are having more than 2 atoms. When you have molecules more than 2 atoms, they may or may not have the permanent dipole moment. If you have the molecules more than 2 atoms, either they may have the permanent dipole moment or they may not have the permanent dipole moment. That depends purely on the geometry of the molecule. We cannot say like that. That depends purely on the geometry of the molecule. So geometry of the molecule is nothing concerned with the shape of the molecule, which may be a linear geometry or bending geometry of the molecule, right? So I am just giving an example of carbon dioxide molecule. Carbon dioxide molecule is having 2 equal C double bond O bond. So if you see this carbon dioxide molecule, C double bond O, C double bond O, right? So one side, this side also dipole moment is there, this side also dipole moment is there. It is a linear molecule, right? So what will happen when you have 2 equal carbon double bond O bond dipoles? So since it is a linear molecule, the bond dipoles will cancel each other. The bond dipoles on both the sides will cancel each other and there is no net dipole moment. There is no net dipole moment for carbon dioxide molecule, right? So this is the case of linear geometry of the molecule. Whereas when you go for the bending geometry, for example, water, if I take, the hydrogen is here, oxygen is here, another hydrogen is also there. The geometry is in a bending nature, right? So here they also have 2 equal HO bond dipoles. In case of water, since they have the bent geometry, what is the possibility here? When you take the bent geometry, the vector sum of the bond dipoles does not cancel. When you take the bent geometry, the vector sum of the bond dipoles does not cancel each other. So this is an added advantage for us. So water molecule is having a permanent net dipole moment. Carbon dioxide does not have the net dipole moment, whereas water molecule is having a permanent net dipole moment. Why? Because of the bending geometry nature. Polyatomic molecules are the molecules which are having more than 2 atoms. Basically, the important thing what you should remember in case of IR spectrophotometry, we should look for the change in dipole moment on the vibration, not the net dipole moment. Especially when you go for the higher molecules like polyatomic molecules where the number of atoms are more than 2. So there we have to look for the change in dipole moment. Definitely the molecule will absorb infrared radiation rather than considering the net dipole moment. This is one of the important feature you should remember in your mind, right? Now the modes of vibration taking place in diatomic and triatomic molecule. What is the various modes of vibration taking place in diatomic and triatomic molecule? So particularly for diatomic and triatomic molecule, there are 3 n degrees of freedom. That is basically translational, rotational and vibrational pattern. So the formula for calculating the number of possible mode of vibration in diatomic and triatomic molecule is given by the formula. The vibrational mode is equal to 3n minus 6. What is this n? N is the number of atoms. So we have the formula, the vibrational mode for diatomic and triatomic molecule is 3n minus 6. So I can take one example here. I take the water molecule. Water molecule contains how many bonds, how many atoms? 3 atoms are there. 2 hydrogen and 1 oxygen atom. So number of atoms is how much? 3. So 3n minus 6 means 3 into 3 minus 6. 9 minus 6 is equal to 3. So how many possible types of vibration pattern is possible for water molecule? There are 3 possible modes of vibration. What are all the 3 modes of vibration? One is the symmetrical stretch vibration. Another one is the asymmetrical stretch vibration. And the third vibration is scissoring vibration. These are the 3 vibrational possible modes for water molecule, right? Now when I go for talking about the linear molecule, for example, if I take the linear molecule cannot rotate about the bond axis, right? We have 2 axis of rotation, so they don't have rotate about the bond axis. So in case of linear molecule, the possible mode of vibration, if you want to calculate, the formula will be 3n minus 5. This is the formula we are using. And as I told already about carbon dioxide is a linear molecule. If you take the carbon dioxide, totally 3 atoms are there. So 3 into 3 minus 5, it is equal to 9 minus 5, 4. 4 in the sense, you will have the symmetrical stretch, asymmetrical stretch, scissoring, Additionally, you will have one bending vibration also. Therefore, 4 possible modes of vibration are possible for carbon dioxide, especially when you do the far IR spectroscopy. Is it clear? Because gaseous molecules we can easily analyze with far IR spectroscopy. So you will be getting one extra bending type also. 4 possible modes of vibration are possible, right? So this is all about the various modes of vibration pattern taking place in infrared spectroscopy, and that too particularly with relevant to the fundamental vibrations of stretching and bending.